Beta decay is exactly like we just explained the alpha, but in this case they are losing a beta particle. A beta particle is a particle that has no mass and it has a negative charge. So we're going to follow the same examples that we did before. We write the incomplete equation. After that, we check the mass. And then after that, we check the number of protons, and the last part will be to determine the missing element. So for example, when potassium goes under beta decay, we lose an electron, electron here, so will be negative. So we put 20 here. 20 minus 1, that's 19. Mass remains the same. Element number 20 is calcium. So let's look at this problem. Beta decay of cobalt 60. Cobalt 60, and the atomic number is 27. So cobalt is losing a beta particle. A beta particle looks like this. So what do we do next? 60, and this is 0, therefore the mass of the particle is going to be 60. And this side is 27. This side has to be 27 as well. So we need to put 20A. Why? Because 20A minus 1 will be equal to 27. Then we look at the particle, that the element that is number 28, and that is nickel. The positron emission is a proton that is converted into a neutron and then a positron. So when we are doing the positron emission, we have no mass and a positive charge. Gamma radiation is just energy that is emitted from a very unstable nucleus. Notice here 99m, and then the mass number passes to 99 because it's just showing that is emitting gamma radiation. The summary is here. Alpha particle, the new nucleus is going to be a new element. Beta looks like this, the new nucleus is going to be a new element. Positron looks like this, it's a new element, but when we emit gamma, is the same element but is more stable. The last part of this chapter is going to be about half-life or a radioisotope. What is the half-life? The half-life is the time that it takes to decrease to 1/2 of its original value. So for example, if we have 20 milligrams, half-life will be the time that it takes to get to 10. The 2 half-life will be to get to 5, and 3 half-life to get to 2.5. Dividing these always by 2. So in a decay curve, we show how pass from half and then half, 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 and like that. So if, for example, a radioisotope has a 40 milligrams, it decays to 20, that is half of it, that will be the half-life. After 2 half-life, it's going to be now 10 milligrams, and then after 3 half-life, it will be half of this, which is 5. So the type of problems that we're going to see here are very similar to this one. So we have P32 is a radioisotope, and it has a half-life of 14.3 days. If we have 8 milligrams of these, how many milligrams we'll have after 42.9 days? So in order for us to solve these problems, we're always going to approach it the same way. We take the time that we're asking, and we're going to divide that by the half-life. And that gives you a value of 3. What do we do next? Well, that's 3 half-life. So we started with 8 milligrams. After 1 half-life, it will be 4. After 1 half-life, it will be 2. And after one more, it will be 1 milligram. Why am I going here? Because there are 3 half-life. 1, 2, and 3. This is a table that shows several radioisotopes that are commonly used for medicine, for example, chromium, iodine, iridium, and some occurring radioisotopes, carbon-14, radio-226, and so. So with this, you don't have to worry, you don't have to memorize this table. The only part that you need to memorize is the type of radiation: alpha particles, beta particles, positrons, neutrons, and gamma.